Yes, good
Good
evening,
evening
everybody.
to all of you.
Yes,
Can you
yes,
hear me?
yes. So, yes, Professor Alam, I welcome you to start your lecture and please start. So, nothing to say more about you because today is the day 6 of your lecture. So, please start.
Can you hear me?
Yes. Now it is fine.
Hello.
Yes,
Can you hear me?
yes, it is fine.
Okay.
Yes, sir, it is audible. You are audible.
Okay. And you can see the screen also?
Yes,
Okay. Okay. So let me start then.
yes. Please
Okay.
start.
So we have yesterday, just let me recapitulate very quickly what we have done yesterday, that we have calculated the propagator uh, the propagation amplitude for a particle which is going from y to x by this quantity dx minus y, and the other was from x to y. So just from y to x and x to y. And we have shown yesterday that for a space-like domain, in the space-like domain, the 4-vector goes as, the 4-vector square should be negative. And if you can make a particular choice that temporal component you take 0, and then the spatial component counts with a negative, so a negative of some squared quantity. So this kind of choice will give you a space-like domain. So x minus y, if I put temporal component equal to 0 and x minus y, then dx minus y minus dy minus x, because dx minus y, if you remember, I have calculated in third or fourth lecture probably. And then this quantity becomes like this. And I have taken x0 minus y0 equal to 0. So from here, the temporal component will go away. I will have only the spatial component. And in the spatial component, I keep the first term of this same, and in the second term, I change the variable p2 minus p. If I do that, in this integral measure d cube p and by 1 by 2 ep, nothing will change, because ep, the energy, is a function of square of the momentum, and d cube p will not change. So only change will come from here. It will just, if I make a p2 minus p, it will become just plus, and then this term will cancel and give you 0. So the probability amplitude for a particle in the for the space-like interval will be 0. That means if you have 2 points x and y which are not causally connected, the propagation amplitude for such interval will be 0, because the probability amplitude from y to x will exactly cancel by the probability amplitude from x to y. So your causality will be restored. And here, how the causality is restored by you can see the causality is restored by the quantum field theory. Then we have discussed in detail the Feynman propagator. By Feynman propagator, what we mean is actually is the vacuum expectation value of the two fields, phi x and phi y, with a time ordered product. This time ordered operator, or sometimes it is called also chronological operator, this will be phi x phi y if the temporal component of x will be more than temporal component of the y, and it will be otherwise if the temporal component of y means y0 is greater than x0. Then what we did, actually we have assumed that this Fourier the Feynman propagator is giving by this integral, and I have argued that this is nothing but this dfx minus y Feynman propagator is nothing but the 4-dimensional Fourier transform of I by p square minus m square plus I epsilon. So this is the Fourier Feynman propagator in the momentum space, and that propagator we have seen has p square minus m square plus I epsilon. I can write this as a p0 square minus p square plus m square plus I epsilon. I am just repeating this because yesterday some students said that I was little fast, so just very quickly I'll recapitulate this. So then P0 square minus P square plus M square is again energy square, I know that. So this P0 square minus EP square is equal to plus I epsilon is the denominator of this integrand. Now, in this integration, in this integral, I have two poles. One is as equal to P0 equal to plus EP, and other one is at the minus EP. But this I epsilon, what it will do, it will shift the pole just above and below the real axis. That is what I have shown you very clearly there, that the pole is at P0 square equal to EP square minus I epsilon. And if you take the square root, then you will see that poles are at plus EP minus I epsilon, and then other pole is at minus EP plus some small quantity proportional to epsilon. So you have a pole just above the negative real axis, and other pole will be just below the positive real axis in the real P0 imaginary P0 plane, complex P0 plane. Now, but this integration to evaluate this Feynman propagator, I need to do the integration over dP0, which is a real quantity. So when I do this integration, I'll have the variation of P0 from minus infinity to plus infinity along the real axis. But if I want to use the contour integration techniques, then I have to close the contour, right? I have to get a closed contour, and I should do it in such a way that I should choose the contour in such a way that only in the entire contour, only the integration along the real axis should survive, and the other part it should vanish. And then we have argued that if the x naught is greater than y naught, right, then how should I in that case, how should I choose the contour? Then e to the minus I P0 x naught minus y naught, this is coming up here, and x naught is greater than y naught. That means this is positive, and this P0 I can write in the upper half plane as real P0 plus I imaginary P0, right? And since x naught is greater than y naught, if you do the algebra, you will see I will get a quantity imaginary P0 times x0 minus y0. So in the upper half plane, which is indicated by this plus sign, and x naught is greater than y naught, this is positive, this quantity will not vanish if I choose the contour in the upper half plane. But that's what I don't want. I want that my integrand should vanish in all other parts of the contour except this real axis, because that is the integration I want to perform. But if I choose the contour in the lower half plane, then you see the lower half plane means in the lower half plane it will be a real P0 minus I imaginary P0. If you do that, then you see the imaginary part comes as imaginary part of P0 x naught minus y naught. This quantity is positive. This quantity is positive, and this imaginary P0 is coming with a negative sign. So in the lower half plane, if I choose the contour, then in this contour, this integrand will vanish. So that is the contour which I should choose. So you see this x naught greater than y naught, if I impose that condition, then I should, when I do the integration, I should choose the contour in the lower half plane, so that in this part it vanishes and I will have the values along the real axis only. That is what I want. And then what I did, so if we do that lower half plane, then you see only pole which is enclosed within this contour is this particular contour just below the positive real axis. So I have to calculate the pole there, residue there. That residue I have calculated, and then the residue times 2 pi I times the ratio is the value of the integration, and then we got this value of the integration. Now the other case I have argued that if x naught is greater than y naught, then obviously x naught is less than y naught, then obviously you can again give the same argument and show that I need to choose the contour in the upper half plane. And in the upper half plane, then this pole will be only included, and the residues in this pole again you can calculate by using the standard techniques of the complex variable, and you can calculate this particular quantity, and if you do the similar integration, it will come like this. So now we know that the Feynman propagator in the momentum space as I said, it is simply I by p square minus m square plus I epsilon, because when I am taking this in the momentum space propagator, then I am getting back those two propagator which I have calculated in the third lecture probably. One is dx minus 1 and other is dy minus x. So in the momentum space, my propagator is, Feynman propagator is this, and this is very important because I will be using this when I will be calculating the Feynman diagrams to evaluate, estimate cross sections, decay rates and all that, which will be connected to the quantities which you measure in the laboratory. And then I again argued that this propagator is nothing but the Green's function for the Klein-Gordon equation. The Klein-Gordon equation is this, del mu plus m square phi equal to 0. Now, by definition of the Green's function, we know that Green's function is defined as the solution of the differential equations. Suppose I want to find out the Green's function of this particular equations, then by definition it should be the solution of this differential operator with the source replaced by the unit source. So this is the definition of the Green's function, right? Now what I did, I just simply took the Fourier transform of this equation, and that Fourier transform, because if you have a derivative, then I know that if I know the derivative Fourier transform of g, then the Fourier transform of this quantity will be just minus p square times, because you have two derivative, minus p square times the Fourier transform of the g itself. So this is the momentum space, Green's function for the Klein-Gordon equation. Multiplied by this is nothing but the propagator. So the free particle propagator is simply the Green's function of the Klein-Gordon equations. And same thing will be true for when you do the quantization of the Maxwell field. There you will see there are some complexity there because of the gauge freedom, but it is essentially, it will be the propagator, Green's function of the Maxwell equations that will give me the propagator. Of course, there will be some gauge choice and all that we will discuss. And similarly for the Dirac equation, the Green's function of the Dirac's equation will be the propagator for the free electrons or positrons, okay, because they are the particle and antiparticle of each other. And this exercise of this quantum integration, as I mentioned, you have done when you have studied the classical electrodynamics, and it is very clearly worked out in the book by Jackson. Okay. So now this part I have done, and I think I was little quick there because I have already discussed this in yesterday. Okay. Now after that, what we have done, we have discussed the Schrodinger and Heisenberg and Dirac picture. This part I hope it is understandable to you because I have discussed it in detail yesterday. And what the argument what we have given here is that the evolutions of the operators only due to the interactions we need to know, because we want to understand the system when it is interacting. So and the evolutions due to the free part of the Hamiltonian we have washed out by through a unitary transformations by going into the interaction picture or Dirac picture. This part, unless you have any problem, I will skip. But let me know if any of you have any problem. So I am not discussing this part because I discussed in very detail yesterday. Okay, and solve the equation. This part I have done yesterday in detail, and my notes which I have sent today contains all the details how it is done. And this is very important if you want to understand the Feynman approach to perturbative approach to quantum field theory, and how the Feynman diagrams will originate. That will also come from there. So this part is important to understand. Now, what I have yesterday also discussed is the started the Weeks theorem. Okay, so please remember from here only that the S matrix which I have calculated yesterday is this expression I have calculated in detail, and my notes contain each and every step of this S matrix. And so let me assume that it is okay, and then let me proceed to the new topic today. And very briefly, let me just tell you is that I discussed yesterday the weak theorem. Why I need to discuss the weak theorem? Because because the reason is very simple. Yesterday I have argued that the S matrix, which I have calculated, that S matrix contains a time order product. See, each interaction, the interaction Hamiltonian at x1, point x1, and the interaction Hamiltonian at point x2 with a time order product. Now, how to, so there are two operators, one is the composite operators H1 and H1, interaction HI, interaction at point x1 and x2, they are time order product, right? That is what is involved there. So we need to learn how to handle time order product or chronological product of two operators. To discuss that, we need the help of the Week's theorem. So while introducing the Week theorem, it may be quite new to some of you, especially to the student. What I did here is that I have calculated some Gaussian integrations, okay? And then in this Gaussian integration, I evaluated this in detail, and I have shown you that this particular Gaussian integration e to the minus alpha x square by 2 into dx, which I call it I alpha, right? I evaluated and got the result, which is this, right? Now, if you, this was your I alpha. If you take a derivative of this with respect to alpha, you get a x square here. That means if you get an expression x square times this Gaussian again, so that is something which is proportional to the average value of x square. So this average value of x square I get if I take the derivative of I with respect to alpha. And I know what is I alpha here. So then I can take the derivative of this, and I can calculate this average x square value. I don't have to do the integration again. If you want to calculate the x4 average, you can take derivative twice. Then I will also take the derivative twice here. You can then calculate the average value of x4, x6, x8, and all that. And then we have shown you that average value of this 2x to the 2n, right? Suppose you have the x to the 2n will be nothing, but it will be proportional to the 2n minus 1 double factorial, right? And then we have also argued how to understand this result 2n minus 1 double factorial, and I have told you that this is nothing but the number of ways you can connect 2 points out of 2n points. So you have 2n number of points. Then what is the number of ways you can connect these points pairwise? And then that number will be 2n proportional to the 2n minus 1 double factorial. Okay. This also I have discussed. And with an example, I have showed you that x to the 6, right? The x to the 6, I can write as product of 6x, right? You can just get an idea that when I calculated the propagator, I have calculated the product of 2 phi x and phi y. Now you can have 4 phi's or 6 phi's involved in a particular case. So then when you calculate their average value, you need to know this technique, which I will elaborate later. So 6 to the x to the 6 I can write as a product of 6x, right? And then you can just see how I can pair them. I can pick up one, then I can choose other x in 5 ways, so 5. Then I can, so 2 gone, since I have connected pairwise. I can take the second one, and then out of 3 I can choose any of them. So 3 ways, 5 into 3 into 1, which is 15, and which is also the factorial 5 double factorial. So that is how we can calculate the average value of any power of x in this particular way. Now this result I will be using little later when I will be discussing the Week's theorem. Now let us go back to not the x, let us go back to the field phi, and let us see how this analogy we can use. Now, as I said, I want to calculate the time order product of phi x1, phi x2. Let us say I have phi up to phi xn, right? I want to calculate the time order product, right? If I want to, the Weeks theorem will help me to calculate this. First, let me start with n equal to 2, right? And then phi ix, you know, this I subscript is telling me that this phi is in the interaction picture or Dirac picture, which I have elaborated in detail yesterday. Now, this phi is in the, and you also remember this phi is evolved by the free part of the Hamiltonian, right? Free part of the Hamiltonian. So this phi I know that this phi I can expand in terms of the annihilation and the creation operators, right? I have written this expression many times. It is d cube p by 2 pi cube 1 by 2 ep to the minus ip dot x plus ep dagger e to the plus ip dot x. So this phi x I can expand in terms of annihilation and creation operators. Now, you know, when again I am just telling you that when I will be discussing the Feynman diagrams, this will be very useful again, because when a incoming particle comes, right, interacts and produce some new particle, that means the incoming particle is annihilated and the outgoing particle is created, right? So this will play a role for in constructing the Feynman diagrams, because after all, the particle which is coming, they are getting killed, and what are produced, they are created. So this expansion, I will show you how it plays a role while considering the Feynman diagrams. Okay, so that will come later, but let me mention you that this we have to consider, because ultimately, though it looks somewhat abstract now, but it will give you some physical quantity. Okay. Now for n equal to 2, I am considering, so I have 2 phi x and phi y, let us say. I want to calculate this time order product, and this phi I break into 2 parts, phi plus and phi minus, where phi plus is the part which contains the annihilation operator. See, plus I have associated with the annihilation operator, and the other part because it is associated with the creation operator. So as you know, the phi contains 2 operators. Its expansion contains 2 operators. One is annihilation operator, other is creation operator. The part which contains the annihilation operator, I am calling it phi plus. This is just a notation. And the part which contains the creation operator, I am calling it phi minus, right? So this is, we should also remember. We should also remember the phi plus, if it operates on vacuum, should give me 0, because phi contains the annihilation operator, and annihilation operators operating on the vacuum should give me 0, because by definition in vacuum there is nothing to kill or annihilate, so it will be 0. Okay, so this, please remember that if I have an annihilation operator or phi plus, right, directly operating on the vacuum, it should give me 0. This is very important. I'll come into and you'll see why it is so important. Now I am evaluating the time order product of 2 scalar field, phi x and phi y. And you know that by definition, the time order product is phi x into phi y if x naught is greater than y naught, and it is phi y phi x if y naught is greater than x naught, where x naught and y naught is the temporal component of x and y 4 vector respectively. Okay. Now this t phi x phi y, I can, for the case of x naught greater than y naught, it is phi x phi y. So I now break this phi x and phi y as phi plus x, phi minus x, phi plus y, and phi minus y. And remember, this phi plus contains the annihilation operator, phi minus contains the creation operator. Similarly, phi plus contains the annihilation operator and phi minus the creation operator. So I just do the multiplication. And if you do the multiplication, you get these 4 terms, which is written in these 2 lines. And in the next line, what I do, I just add a term and then same term I subtract. So I have just added a 0, right? Why I am doing, I have done that because you see, this underline these terms, these 2 terms, I can write these 2 terms combinedly as a commutator, phi plus x and phi minus x. Okay, this is the commutator. Okay, now you see the all other terms, if you note, just simply phi plus x, phi plus y, phi minus phi plus, phi minus phi plus, and phi minus phi minus. This is we can make a very important observation here. You see, in a term, wherever there is a annihilation operator, wherever there is an annihilation operator, that operator is the right. Operator here. Here, phi minus contains the annihilation operator, but plus contains the phi minus contains the creation operator, but phi plus contains the annihilation operator. So phi plus on the right. I have not done any manipulation. I have just simply written the product. Only thing what I have done, I have just somewhere where I have a creation operator on the right, that I have taken into account to a commutator, right? To a commutator. And all other terms, in all other terms, the annihilation operator is always on the right. And this term phi minus, there it is always in these two terms there is creation operator, both are creation operator. So I cannot do anything because no annihilation operator is there. So my point here is that the terms where any annihilation operator is involved, that is always on the right. And when you do that, when you arrange the operators in such a way that annihilation operators are always on the right, that is called normal ordering. That is called normal ordering. So suppose you have time order product of two fields. What I have done, I have written them in normal ordering, right? Normal ordering plus a commutator. And this will help me. And this is precisely actually is the we are going towards the this will be very useful for the construction of the Feynman diagrams. Okay. Now this is normal ordering, and I will show you through a simple example the importance of this normal ordering. Now that means the normal ordering means that if I have operator, let us say AP, AK dagger, AQ, where AQ, AK dagger, this is the creation operators, other are annihilation operators. When I operate in this normal ordering, what will happen? This AP, which is a annihilation operator, should come on the right of AK, and that is what is normal ordering. So it has just come there. Now, you should all remember here one important point is that I can do that because I am doing, I am working for a scalar field or field which is associated with the bosons. If they are fermions, then these operators you will see later that they will anti-commute. If they will anti-commute, then there will be a negative sign coming here, right? When you normal ordering, then when you are making a change in the order of the operator, a negative sign will come, because in case of fermions, the operators they anti-commute, and that anti-commutation comes automatically, because unless you take the anti-commutation relations, you will see that energy or free energy of the Dirac Hamiltonians will not be positive definite. So that's a very important point, that anti-commutation you have to take when you quantize the fermionic field, right? Now, and that anti-commutation relations will obey the Pauli exclusion principles. Okay, so Fermi-Dirac statistics will be built in through the anti-commutation relations when you discuss the fermion fields. But here, since they are bosons, interchanging between the two operators will not make any change in the sign. That's a comment I would like to make here. Now, so this time order product of two field, phi x and phi y, this I have written in such a way that wherever there is a annihilation operator, that is on the right. That is what is called normal ordering, and rest is a commutator. So this time order product phi x phi y, I can write that notationally as this, 2 dot phi x phi y, and again this here colon, right, plus a commutator. This commutator was there already, that commutator, and this sign, this colon sign on both sides of this phi x phi y indicates that I have done the normal ordering. This is the notation, nothing else. This is actually a short way of writing this long expression, nothing else. Okay. So this is how it works. Now, let me just tell you Let us understand what is the normal ordering means through an example of the harmonic oscillator. Okay. So, you know, the harmonic oscillator we have discussed, right? So the Hamiltonian for the harmonic oscillator H, right? You know, I have shown you that the Klein-Gordon equations, right? When I took the Fourier transform of the Klein-Gordon equations with respect to the spatial coordinate, I have shown you that that is actually gives you an infinite number of harmonic oscillator modes, right? That is what we have done. And then we use extended the techniques which you use in non-relativistic quantum mechanics to calculate the Hamiltonian and quantize the field and calculate the Hamiltonian. And that Hamiltonian we have calculated as d cube p by 2 pi cube, EP, the energy, which is root over p square plus m square, AP dagger AP, creation operators and annihilation operators, plus there was a Dirac delta function with argument 0, right? This has originated from the commutator of the two operators AP and AP dagger, which AP dagger when momentum when both the annihilation and creation operators will have the same momentum, then you will get a Dirac delta function. And you know, this is just simply the number operator, right? Now, just we have defined the vacuum, that annihilation operators operate on the vacuums and give you 0 for all p. Now, this H, if you operate the H, right, the annihilation, the Hamiltonian on the vacuum, right, this will give you 0, right, because the annihilation operator operating on vacuum will give you 0. And then this term is anyway infinity, because d cube p by 2 pi cube EP into delta 3 with argument 0 is infinity. This is infinity, and I'll show you this is also infinity. So let us first consider what is the origin of this divergence, delta in 3 dimension with argument 0. By definition, you know, Dirac delta function is nothing but it is the Fourier transform of unity. So just one is sitting here. I have taken the Fourier transform. That means I have taken 1, I have multiplied by to the p dot x with 1 and integrated over d cube x, right? This if you do, then you will get Dirac delta function with momentum variable p. Now here you have the argument 0, so I put p equal to 0. So if I put p equal to 0 here, then what happens? This just becomes d cube x. This will vanish. D cube x means it is the volume. So this divergence originates. This divergence originates because the space is infinitely large. So if the space is infinitely large, then because of that you are getting this divergence, right? That is one divergence. The other factor is d cube p by 2 pi cube into EP, right? The energy. Let us see. So d cube p by 2 pi cube into EP, I can write that 0 to infinity. D cube p I can write 4 pi p square dp, because there is no angular dependence in the function which I am integrating, which is simply root over p square plus m square, where p is the 3 vector here. Now this integration, if you simplify, it will become 0 to infinity p square dp from this integrand, and then what you have here is square root of p square plus m square. Now you see that this will diverge. This will diverge because if you integrate this and put the limit p equal to infinity, this will certainly diverge, right? Now this divergence is coming because the momentum can go up to infinity. This divergence when p goes to infinity is called ultraviolet divergence. Ultraviolet divergence. And ultraviolet divergence is originated from the fact that when you are taking p tends to infinity, then you are trying to probe arbitrarily small distance, right? Because p tends to infinity will make you the spatial variable x goes to 0. So this ultraviolet divergence is originating from the fact that if you want to probe arbitrarily small distance, then this kind of divergence will come into the picture. Okay, but you can argue here is that no theory can be valid up to momentum infinity, right? All theory will have, you know, some limitations, right? And so this ultraviolet divergence is coming because of this particular particular point is that if you want to prove arbitrarily small distance, right, you need momentum tends to infinity, and in that case it will go to infinity, right? So this is one thing. So that is what I have written here, that this divergence is encountered because we have assumed that the theory is valid up to arbitrarily small distance, and that cannot be true. I mean, no theory can be true for arbitrarily small distance or arbitrarily large momentum. And this for the ultraviolet divergence, you can cure by in the interaction theory by a standard procedure which is called the renormalization procedure, and it's a very mathematically rich and extremely to some extent it is a complex process you have to go through, but it is very interesting. It gives a very interesting result, like when you in the leading order the Coulomb potential, we write is as E square by R, right? But if you at very small distance, is the potential E square by R? It's not. Up to one loop calculations, one can show that E square by R Coulomb potential will have a correction in terms of Dirac delta function. So at arbitrarily small distance, the Coulomb potential is not E square by R, right? It will have a correction term, and that correction term is actually sometimes, not sometimes, that correction terms helps you to understand the Lamb shift in the atoms. So it has a physical origin also, and those kind of risk physics will come if you go to higher order calculations or root calculations in quantum field theory. So from the first principle, you can calculate what should be the correction to the Coulomb potential E square by R through that renormalization procedure. But that's a matter of the advanced course. Let us, for the time being, not discuss that part. But let me just tell you the meaning of the normal ordering. Okay, so that is the purpose I am discussing the harmonic oscillator, and I have already told you that infinity is coming in the harmonic oscillator, and the reason for that. Now, can we get rid of that infinity? Let us see that. So here I have written down the Hamiltonian for the harmonic oscillator. It is H equal to P square by 2m, but m I have taken 1 just for simplicity, omega square by 2 x square. This is the harmonic oscillator potential. This I can write as H equal to half P plus I omega x and P minus I omega x. And I don't have to do anything for that, right? Because I can write it in this way. And this P, X and all that, these are just like as if the classical, if they are classical variables, then I can, multiply them. And if they are classical variable, I can show you that this xp and px, they will then commute. It will become 0. And again, you will get back. If you evaluate this product, you will get P square by 2 plus omega square x square by 2. Now, this H equal to this. So this is the correct expression. Now, at this point itself, I promote the dynamical variable x to as an operator in terms of annihilation and creation operators, and momentum also I promote as a operator in terms of the annihilation and creation operators. Now I can invert these two relations and write A in terms of P and X operator and A dagger in terms of again P and X operator. Now you see what has appeared here. Now what I do, this Hamiltonian, now I promote them to operators, right? P and X. And you see, this is just this P minus I omega x. This is just the annihilation operator with, of course, a constant. And this P plus I omega x, which is just the creation operator. So if I just put it, you get H, the Hamiltonian, you get omega A dagger A. If you have not worked in natural unit, you will have H bar omega A dagger or H bar omega N, where N is the number operator. Now the question is, where is the 0 point energy? Where is that half H bar omega? Where is that 0 point energy? It's not there. Why it is not there? Because you see, I have manipulated in such a way that the annihilation operator on the right? The annihilation operator on the right of the creation operators. Is it true? Let me see. Let me just show you that it is. Hamiltonian again, I am writing in this way. Now, what you do from here itself, you promote the momentum and the coordinate x to the promote them to operators. And now you put p from, where is that, from this expression and x from this expression, right? It will be minus half omega y2 because you have a p square, so it will be a minus a dagger square, and here again you have a x square, so a plus a dagger whole square, right? Now you just break this square. Remember that a and a dagger, they do not commute. If you do that, you will get h is omega by 2, a dagger, and plus a dagger, right? Now I know that a and a dagger, they satisfy a commutation relation, right? This is the commutation relation. So what I do, I can write this a dagger by using this commutation relation. A dagger equal to omega, right? So if you have a h bar, then h bar n h bar omega plus h bar omega by 2. This is the 0-point energy. So this has appeared. Again it has come back to your system, right? But then the question is, why it has not appeared here? Because I have cleverly written the Hamiltonian in such a way that my annihilation operators come in the right of the creation operators, right? So this is all. So so what I am trying to tell you here is that if you normal order your operators, then this 0-point energy will not come into the picture. Now let me make a few comments here. You can say that, well, that doesn't harm the theory because we always make the difference in energy. So if you have a common energy, which is 0-point energy, then it will just get subtracted out, right, in the transition, right? But you know, the as I mentioned there, that 0-point energy is not appearing if I am writing everything in the form of the normal ordering. But if you and it is not harming your system because, as I said, that you are always measuring the difference in the energy. This is not within our part of the core discussion, but let me just make a point here that, you know, but this vacuum contains this energy. Let us say h bar omega by 2 for this particular system of harmonic oscillator, right? And then, you know, the gravity actually should be able to see everything. Any energy, any energy should be seen, quote unquote, seen by the gravity. Why? Because, you know, if you look at the Einstein equations, right, R mu nu, the Ricci tensor, half minus half G mu nu, trace of the Ricci tensor, equal to minus 8 pi G gravitational constant T mu nu. This is the energy momentum tensor or trace energy tensor, plus a term lambda G mu nu. This lambda is the famous cosmological constant and G mu nu is the metric tensor. Now this energy momentum tensor is a source of, you know, gravity, right? So this acts as a source, source term for the gravity, right? And that is responsible for the space-time curvature, right? Now this, if you have a vacuum energy, that vacuum energy should contribute to this energy momentum tensor or this stress energy tensor, and then gravity should be able to see it, right? Now, you know, also you have heard that, you know, currently that our universe has 72%, about 72% dark energy, right? About 23% or 4% dark matter, and rest is the visible matter, right? And that dark energy has the characteristics of this lambda, right? Now, whether this lambda or that vacuum energy is contributing to this lambda, right? That is a question you can ask, but then the value of lambda is very small, 10 to the minus 3 electron volt to the power 4. You see, this has the dimension of the energy density, because in our unit, energy or mass is inversely proportional to the length. So I can keep 1 electron volt here, and electron volt to the cube I can make as L to the minus 3. So it will be EV by L to the 3. That means it will have energy per unit volume. So this has the energy density, which is very small, 10 to the minus 3. But the particle, if the 0 point energy of all the particle physics particle interactions will contribute to this lambda, then this should be huge. Now the next question should be, then is there any cancellation of the vacuum energy? Let us say between the vacuum energy of bosons and fermions, is there any fine cancellation so that they are not contributing additively? That we don't know, right? And this problem is the famous cosmological problem. Okay. So this is just a comment. What I wanted to make here is that that if I write down my operators in a normal ordering form, then I can get rid of the 0 point energy. And as I have shown you through the example of the normal ordering in the harmonic oscillator problem, in fact in the MSc course, this should be introduced, and so that students should start thinking about this. Okay. Now let me, so what I have shown you that in case of, by giving the example of the harmonic oscillator, that 0 point, and we can get rid of this 0 point energy by normal ordering the operators. Now let us go back to the again this time order product of the phi x and phi y, these two field. So this two field is, again, this is the notation for the normal ordered part as I discussed earlier, and this is the commutator which I have derived this expression. Now, and this expression I have got when derived when x naught was greater than y naught. You can follow the similar step and show that for y naught greater than x naught, it should be phi plus y and phi minus x. This is obvious, just y and x will be exchanged, right? Now what I will define in this phi x phi y, this sign here, sometimes this sign is also put above. This is sometimes in some book it puts below, some it is up, or sometimes mixed also. They do this phi x phi y. We define this commutator part as by this notation, that phi x phi y, and this is called contraction. When I write this way, then I am meaning that phi x and phi y, these two field has been contracted, right? Like the Week's theorem, when I gave you the example of the Gaussian integrations, then I said that you have two endpoints, right? How many ways you can join them in pairs, right? This is like joining in pairs, which we call contraction, right? So how many? So suppose you have 2n number of fields. What is the number of ways you can contract them, right? So this is called contraction of two fields, phi x and phi y, and it is actually defined by phi plus and phi minus this commutator. And this commutator is, I am not just writing arbitrarily, I have derived it in the earlier slide. Okay. And this phi x and phi y actually is nothing but the propagator. Why I am saying this? Because you go back to your what was the Feynman propagator? Feynman propagator, if you remember, I have discussed that in detail yesterday, and I have just gone through today. It is the vacuum expectation value of this operator phi x and phi y, right? So there is two vacuum there, vacuum 0, this and this side. So if I take the vacuum expectation value of this left hand side, that is my Feynman propagator. Now vacuum expectation value, if I take on the right hand side, this part will give me 0. And you know why? It will give me 0 because this is normal ordering, and annihilation operator is always on the right of the creation operator. So when the annihilation operator is on the right, and when I take the vacuum expectation value, this annihilation operator will kill the vacuum. So it will give me 0. So this part will give me 0, right? And then only this part will survive, this commutator part. So this phi x phi y, right? This commutator actually, which I am writing in the form of this contraction, it is nothing but the Feynman propagator which I have calculated, right? So this phi x phi y contraction I should write in terms of the Feynman propagator which I have just calculated, delta f x minus y, right? So then what I can do, I can write the relation between now the time ordering and the normal ordering. The time ordering of operator phi x and phi y is equal to normal ordering, right? And within the curly bracket I am putting, and all possible contraction, right? All possible contraction. Now, the term which will be contracted, that term will only give you non-zero contribution. Other term which is not contracted will give you 0. Why? Because this is not contracted means this has annihilation and creation operators. And by normal ordering, the annihilation operator is always on the right. And when I take the vacuum expectation value of that, it will give me 0. So only in the time order product, when I evaluate, only the contracted part will give me non-zero contribution, and the normal ordering part, which is not contracted, will give me 0, because by normal ordering, I mean the annihilation operator is on the right always. And when that will act on vacuum, by definition, I will get a 0. Okay, so this I'll give you an example of this today. Now, in general, if you have a product of say n operators, phi x at 1, phi x2, phi xn, that time order product of n number of fields, I can write as normal ordering of those fields plus all possible contraction, okay. Now, as I said, the term which will remain uncontracted will give you 0, because again the uncontracted term, the normal ordering term, the annihilation operator will be on the right and it will kill the vacuum. Let me give you a small example of that, whether that is really happening or not. Okay. So let me give you an example. So let us take 4 field. Okay. Let us take 4 field. Phi x1, phi x2, phi x3, phi x4. 4 field I have taken, right? And then in this 4 field, so this is the I calculate the vacuum expectation value of the time order product of 4 phi fields, right? Actually, I am going now towards the Feynman diagrams. Okay, so you will see how it is originating today, and then next day I'll show you. But today still I am discussing the free field, and tomorrow I'll so free field is not interesting, as you know. You will not learn anything if you don't have any interaction. But it is important to understand the sort of grammar of this theory. So 0. This vacuum expectation value of the time order product of phi x1, phi x2, phi x3, phi x4, 4 phi's. Time order product, vacuum expectation value of the time order product. Okay. Now, you see, yeah. So you see the time order product of 4 field with all possible contractions, right? With all possible normal, so time order product of the 4 field will be normal ordering of all possible contraction. So first term will be, right, low contraction. That is one possibility. There is no contraction. And in the second term, you will have contraction between the, let me call it x1 and x2, but it is really phi x1 and phi x2. So between x1 and x2, and second one will be 1 and 3. Third one will be 1 and 4, right? Then 2 and 3. These are all possibilities. You just can count it. 2 and 4. Then 3 and 4, right? Now you see, in this all possible contraction, first term, no contraction. That will certainly give you 0, because you will have annihilation operators and creation operators. But when you will take the annihilation operators on the right, that will give you 0. Pairwise contraction of 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, right? And 3, 4. These two are contracted. So this will give you a Feynman diagram, Feynman propagator, because these two are contracted. these two are not contracted. If they are not contracted, they will have annihilation operator again. And when you normal order them, because you have to normal order, n is sitting here, again it will give you 0. So anything which is uncontracted will give you 0. Only there will be 3 terms at the end where 1 and 2, 3 and 4 contracted, 1 and 3, 2 and 4 contracted, 1 and 4, 2 and 3 contracted. So when this happens, then in these last 3 terms, there is no uncontracted field, right? There is no uncontracted field here, right? Since there is no uncontracted field here, so there is no annihilation operators. They are just simply the Feynman propagators, because as I have said already, that the contraction means the contraction is just will give you just the Feynman propagator, right? And uncontracted will have annihilation operators which will give you 0. Like you see this uncontracted term, 1 and 3 you have contracted, so that will give you a Feynman propagator x1, x3. And what does it mean? That particle propagates from x3 to x1. It can also propagate x1 to x3, because Feynman propagator contains the time ordering, both y to x and x to y. So this gives you the Feynman propagator. And then other 2 non-contracted field, phi x2 and phi x4, will remain to be normal order. And when you normal order them, annihilation operator will come on the right and give you 0. So any term in which there is remaining uncontracted operators will give you 0, because when I take the vacuum expectation value, then normal ordering on many operators will give you 0. Therefore, only the fully contracted term they will contribute. And what are those 3 fully contracted terms? Phi x1, x2, right? So that will give you Feynman propagator from x1 to x2, and then contracted x3 and x4. So contracted x4, and then here last term is contracted between 1 and 4. So particle propagation from 1 to 4 or 4 to 1, and the other one is contraction of 2 and 3. So Feynman propagator x2 and x3. So 3 to 2 or 2 to 3. This is the propagator which we get. So now can we show that in graphically? Let us see that we can show that graphically. I have 4 points x1, x2, 3, 4. So I have 4 points 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Now first one is telling me that particle propagation from 1 to 4. So I draw a line between 1 to 4. Oh, sorry, 1 to 2. So 1 to 2. And then another 3 to 4. So 3 to 4 I draw a line. Then here I have 1 to 3. So 1 to 3 I draw a line. 2 to 4 I draw a line. And then 1 to 4, 1 to 4. This is not crossing this. So 1 to 4 and 2 to 3, 2 to 3. So this is the diagrammatic representation of the time order product of this field, right? That is what is the. So these are simply the Feynman diagrams for the free particle propagation. But free particle propagation will not help you to learn anything actually, because if a particle goes from 1 to 2 and other goes to 3, 4 to 4, and if they are not talking to each other, if there is no interaction between them, then we don't learn anything. But this is just a demonstration how the Feynman diagrams is going to arise in our theory. So simply what we have done is that we are calculating the time order product of the combination of fields. Why I am doing this? Because if you remember the scattering matrix, let me just go a little bit back and show you this scattering matrix which I have calculated yesterday. Basically, that this is the scattering matrix. Let us call this S2. This is the second term in the perturbation series. This is product of time order product of 2 Hamiltonian, right? Now the time order product of 2 Hamiltonian, right? This Hamiltonian will contain some combination of fields. This will also contain some combination of field, and I have to take the time order product. So when I'll evaluate this time order product with the interactions, that will give me the Feynman diagrams with interactions. But that will come little later. Okay, that will come little later. For the free field, I have shown you that if you have a time order product of the field, then just it is very simple. The time order product I have written in terms of the normal ordering plus the normal order of all possible combinations, and all these things have been done. But what you have to do, you have to go through it once and feel the that unless you do by yourself, you will not have a feeling. Okay. So this is the how the diagrams will from the time order product of the operator, how the diagrams are going to come into our picture. Now for the with the interactions, now we have to develop the Feynman diagrams when interaction is present, and we have to learn how to draw the Feynman diagrams. Okay. Now this is the right time to have any discussions if you want on this part, because now I will go to the interactions. So if you have any questions, let me know. Because whatever technique I have so far discussed, rest of the things will be simple. Just the time order product of this expansion, if I know, then it will be I mean, it is almost streamlined, so we will be able to do it very quickly. But let me know whether there is any problem.
Sir, I have a small question.
Please,
about
yeah.
the ultraviolet divergence.
Right.
I mean, you said that no physical theory would be correct over a very small distances. Right. So is it because of something back of mind is going on about the quantum gravity, because it allows you?
Certainly that is true. That is true. That is true at very small distance. At very small distance, gravity will be the most dominant interactions, right? And we know how to quantize the gravity yet, right?
Yes.
So that's one thing.
Yes.
That is one thing. I can also answer in some other way. Suppose you have you start with the you start with the interactions of the, let us say, electron and positron. Okay. So at low energy, electron positron will interact, and at very low energy, electron and positron will elastically scattered, right? E plus A minus going to E plus I minus, which is known as Bhabha scattering. Or you can have pair annihilations, pair creations, right? These kind of interactions you can have, right? Now suppose you collide E plus E minus at low energy, then this process you will see this process only, right? All the electromagnetic process. But suppose you collide electron and positron at very high energy, let us say several GeV energies, electron and positron. Then what can happen from electron-positron collision, right? You will be able to produce, let us say, proton and antiproton. But the proton and antiprotons, they are strongly interacting particles, right? So when you are scattering electron and positron at high energy, then producing proton and antiproton or quark and antiquark, then your electromagnetic interactions will not be able to describe the entire process, because only the strong interaction has started playing a role.
Yes. Okay.
So when we say purely electromagnetic process, then we are in the low energy domain where we are creating pair annihilations or creations going on, or elastic scattering on electron positron going on. But very high
actually
energy,
these things actually happens at very high energies.
That's right. So
that means we are probing very small distance scales.
Right. So when you are doing that, then at low energy phenomena you will be able to describe by the electromagnetic interactions only. But the physical phenomena which will be taking place at very high energy scale, you will not be able to describe that by purely electromagnetic processes or electromagnetic interactions. You have to invoke then the strong interaction physics also. So then at certain energy scale, electromagnetic interaction is valid, but it will not be able to describe the entire process. something like that.
Most dominating factor.
Right. So that's so a very small distance, as you said, that it will be a problem. Yeah. So any other question? Because why I'm saying this, because if you have understood up to this now correctly, then my job and your job will be easier next for the next lectures and all, because simply it will be just the time order product of those operators I will calculate and show you how one can draw the Feynman diagrams and cross sections and all that. Okay. So let me have some question if you want. Any question from any participant?
Yes, one question from the in the chat box from Wifat Nasrin.
Okay, let me see.
What is the motivation of weak theorem?
The motivation of weak theorem is, this, when I have yesterday, when I have calculated the scattering matrix, let me just tell you that when I have calculated the scattering matrix, a time order product came, and that time order product of the operators. Now the question is, how should I evaluate the time order product? And Week's theorem tells me how to do that. Now you may ask me how that time order product come into the picture. That I will explain. But let me have some other question. So let me then go and show you how the time order product came into the picture. Okay, so that's I want that, because if you understand this part, no, then my drawing Feynman diagrams and because we are almost done the grammar part. Now we have to, with that knowledge of the grammar, we have to make the sentence correctly. Okay, so let me just go there. Yeah. Yesterday I have discussed this part that. Let me just. Where is that? I have yesterday discussed the three picture of the quantum mechanics, right? One is the Schrodinger picture, where we have started with the Schrodinger picture and shown you that there the time evolution of the states are, given by this Hamiltonian, right? The Hamiltonian, you can say that this is actually the generator of infinitely small time translation. So they are the generators. So the Schrodinger equations, right? Where the states has the time dependence and the operators are time independent. This part I assume that you have learned in your MSc. Okay, but still I am repeating this. And then what we have done in the Schrodinger picture, we have tried to calculate the expectation value of omega s, which is an operator in the Schrodinger picture between the two Schrodinger states, and took the time derivative of that. And when I took the time derivative del psi del t, right? We will have three terms, and this del psi del t, we know that they satisfy this del psi del t. When I take the derivative, del psi del t will come, and that del psi del t is given by this equation. Del psi del t is equal to I del psi del t is h psi, right? So all these del psi I can replace by h psi, right? I have done that, and then when I did that, I got a commutator between omega s and h. Now, this psi, they are function of time, right? So what I did actually, this time variations of this psi is given by this evolution operator to the minus IHT. So what I did here, I wrote this psi, right? Psi t in terms of psi 0 and at the cost of some operator e to the IHT. Did the entire algebra and shown you that I can write down from there the evolution equations for the operator in the Heisenberg picture omega h. And omega h, this definition automatically comes from here, is omega h Schrodinger picture, omega in Schrodinger picture, the operator in the Schrodinger picture, and these are the two time. This is the time evolution operator, the IHT and e to the minus IHT, right? Generators of the time translation. So this omega h we got. This is the Heisenberg equation, which tells you how an operator will evolve with time. And this phi, the scalar field which I am considering here, this is a field operator. So this phi will also, evolve according to this equation, that phi s will, evolve as e to the I, time evolution will be controlled by e to the ist phi times e to the minus ist. Now, what I said here, this h, I have written this h in terms of pre-Hamiltonian plus the interaction, pre-Hamiltonian plus the interactions. H naught plus H int. H int was the interaction. Now, what we argued then, that the evolutions of the operators under pre-Hamiltonian, I want to wash that out from the system, because if the operators evolves only by the pre part of the Hamiltonian, I don't learn any physics from there, right? Because unless I have the interaction, in the system, I'll not be able to learn anything. So what we did actually, we through some unitary transformation, which I discussed yesterday, I have washed out the time evolutions due to the free part of the Hamiltonian. Because, and I argued there that suppose you are studying a scattering experiment where you have a target and a beam is coming from the remote source, and when the beam is at the remote source, that the particles at the source, they are actually like free particles. They are the eigenstates of the free Hamiltonian. So that eigenstate of the free Hamiltonian is coming, hitting the target, having some interactions, and then after the interactions, it is flying a long distance and getting detected in the detector. So when it is starting from the source and getting detected in the accelerating source, and when it is getting detected at the detector, at these two extreme point, they are the eigenstate of the free Hamiltonian H naught. But when it is interacting, right, at that point of time, this interaction, during the interaction time, it is bringing some information which is helping me to understand the physics of the process. So that is why what we have done through the unitary transformation, we have washed out the evolution due to the operator H naught. So what we did there, you have the Schrödinger psi. I have defined this psi in the interaction picture denoted by I, or you can also call it the Dirac picture. So Dirac picture psi is e to the I H naught t free Hamiltonian psi s, right? Now I can take the time derivative of this, right? And if you take the time derivative of this, right, you will get this particular equation, where you see automatically this psi I, the state in the interaction picture or the Dirac picture, right? Time evolution of that is governed by nothing by H minus H naught, but that is just the interaction. Please go through this mathematics, H minus H naught, which is just the interaction. So this H minus H was H naught plus H interaction. So H minus H naught is simply the interaction. So by this definition, when I take the time derivative, I get an equation for the evolution of the interaction picture, but that evolution is controlled by the interaction. But so you see, the ultimately what we got the evolution for this psi I in this particular equation. So the interaction picture psi is evolved by the interaction only. There is no sign of the in this there is no H naught, and that is what we want. How this evolves due to the interaction. This derivation is done each and every step, so you just follow it, right? Now then what we did, we asked the question, how suppose I have interaction picture or picture which will take a state in the interaction picture or Dirac picture from time t naught to t, right? If you do that, then again what you do, you again take the derivative of this and do some manipulations, which all the lines are there and I have discussed it, so I am not repeating it. You get the evolution of the operator u, which is evolving a u, which is, as by definition, which is evolving a state from in the interaction picture from t naught to t, that u satisfy a differential equation, and that differential equation you have only the interaction Hamiltonian, right? Now you have to solve this equation, remembering that both h and u are operators. And this equation, you know, we have solved. I have argued yesterday that any differential equations you can just convert them to integral equations with built-in boundary conditions or initial conditions. So for this particular differential equation, your initial condition was at the same time it doesn't evolve, that so u at t naught must be equal to 1. And if that is so, then this should be your solution, because you see, you just take the time derivative of this, you will get back this equation. It is also satisfying this boundary condition, because if you take t naught t equal to t naught, this will vanish and you will have u t naught equal to 1. And as I argued that this is a integral equations, right, which you have learned in your mathematical physics. This is a Volta type of integral equations of second kind. Why Volta type? Because the integration limit is variable, and it is second kind because the unknown is within the integral sign and outside the integral sign also. Inside and outside, both the unknown is there both inside and outside the integral sign. So this is a second order equation. And then this kind of equation, for solving this kind of equations, that this can be a technique which is called the iterative method. So, you know, so what I did in the iterative method when I solve this particular equation, what I will do first is I will put this u as 1. So first order solution will be u t naught t equal to 1 minus I t naught t hit dt, because I have put here 1, this one, because this is the first order solutions. And if you remember, this is very similar to the what you learned in your quantum mechanics when you solve the Lippmann-Schwinger equation. In Lippmann-Schwinger equations, you have probably learned that when you replace this, you know, it will be like psi phi plus phi v phi, right? Phi v psi. And when you replace that psi by phi, the free plane wave, then it becomes the first born approximations. So this is similar, I mean, the iterative method. So that's what I want to tell you. So, and the second time, so first iteration, you will get this solution, right? And in the second iteration, this is the solution which I'll put in place of u. And then I get this. This is the second order solution. And I go on doing this. If I go on doing this, I'll get the solution of u like this. And you know, what is this u? It is telling you how the system evolves from time t naught to t, right? Now, suppose I take t naught to minus infinity, remote past, and t plus infinity, far future. Then this u and the limit of t naught tends to minus infinity and t tends to plus infinity is nothing but the scattering matrix, because this is telling me how the system is evolving from remote past, where the particle is free, and to the far future, when the particle is again free, when it is getting detected through this interaction hi. So this is nothing but is the scattering matrix. So if you know the scattering matrix, then you can calculate the cross section. So but we have to do it perturbatively. So that is the physical interpretation which I gave. And now one interesting thing you should note here is that when you are doing this integration, right, then the integration limit is from t naught to t and t naught to t prime, right? T naught to t and t naught to t prime. So you see the integration limit in the lower limit is t naught, but upper limit is t and t prime. But if I want to take the limit t naught tends to minus infinity when the particle was free at the accelerating source, and t to plus infinity when the particle is getting detected as a free particle in the detector, then the t and t prime should be same, right? This limit should be same. And to make that limit same, what I did, I have shown you how to do this integration in detail through this diagram. right? So suppose you consider this integration T0 to T and T0 to T1, right? Now, to do this integration, what you have to do, you just pick up a T1, and integrate over T2 from 0 to T1, right? And then you vary T1 from T0 to T, right? So automatically the limit of both the integration, upper limit will be T0 to T, right? Now again I argue that this T0 and T1 and T2 I can just interchange. I can just interchange and get T2 first and T1 second, because that should also be valid, because in this integration T1 and T2 are dummy variable. So when you do that, then while you are integrating again, what you should do, you should pick up a T2. So you should pick up a T2, right? And integrate over T1, right here, integrate over T1 from T0 to T. So if you do that, you will cover the upper triangle, and earlier you covered this lower triangle. So this lower triangle is half of the total square, and upper triangle is also the half of the square. So the two integrations you can combine in this particular fashion. But remember, when you are doing the integration, this part is very crucial. When you are doing the integration in the lower triangle in region 1, you remember that T1 is greater than T2, right? T1 is greater than T2. And where you are in the upper triangle, T2 is greater than T1. So when I am doing the integration, this is the lower triangle, T1 is greater than T2, but in the upper triangle, T2 is greater than T1. And when I am saying that I can do in both way, so that is since T1 can be greater than T2 or T2 can be greater than T1, that is forcing me to introduce a time ordering operator here. That is the whole story. So you see, when I am calculating the scattering matrix, right? Scattering matrix, right? This, because I argued that this my U is nothing but the scattering matrix in the limit T0 tends to minus infinity and T2 tends to plus infinity. So when I am trying to evaluate this integration, evaluating the scattering matrix, it is actually forcing me to have this time ordering, because T1 can be greater than T2 or T2 can be greater than T1, and both are possible, right? So this time ordering operator is automatically coming into my picture when I am trying to evaluate the scattering matrix. And now the next question would be how to handle the time ordering operator, right? How to handle the time ordering operator. And you see the Weak theorem is precisely telling me that the time ordering operator, where is that? This is harmonic oscillator. Time ordering operator. Time ordering operator of two fields is normal ordering of all possible contraction. Now, by possible contraction, I have argued today this contraction is nothing but the Feynman propagator. An uncontracted term, if you have an uncontracted term, that will involve the annihilation operators, and normal ordering will tell you that put the annihilation operator on the left, and you have a annihilation operator on the left. When you operate that on the vacuum, it will give you 0. So Weak theorem is telling me how to handle the time ordering operator in terms of normal ordering plus all possible combinations, contractions. The contraction part is giving me non-zero part, but this part will give you always 0. That is precisely is the role of Weak's theorem. It is just telling you how to evaluate the time ordering operator, right? And that's actually the Weak theorem. And this is the general statement of the Weak theorem, which I have written here. Okay, am I clear? Am I clear?
Yes, sir. Yes.
Nasreen, am I clear? See, the time ordering operator, please go through this derivation of this matrix. the time ordering operator I am forced to put in the scattering matrix. Now the question is how should I evaluate this? Which theorem is telling me how to evaluate it? That's all. Yeah. Any other question? So what I will do next day, I will discuss with you how to draw the Feynman diagrams with the interactions and calculate the cross sections, which you can measure in experiment. Yeah. So let me have some. If I have more questions, let me know that. But to the students, I am telling you, unless you do by your hand, it is not a quantum field theory. As I said, is not a very easy subject. Let me tell you but it's a very fundamental theory. As I said, suppose you want to learn what is the correction to the Coulomb potential. This is the only theory which can give you some answer. Yeah. So please, am I audible?
Yes, sir, you are audible.
Yes, you're
So
audible.
let me know if you have some any other interaction, other question. So is it let me ask the student, is it useful? You find it? You find it is useful? Students, please. Because one can jump and draw the Feynman diagram, but if you follow this procedure which I am doing, you will learn the grammar of and so please let me know if it is. And in this Feynman diagrams, in the quantum field theory, it will give you the dynamical informations of the information on the dynamics of the process. And for any physical process, you have two things to consider. One is dynamics, other is kinematics. It is like suppose you play cricket, and suppose you are a batsman, you will get a run if you can properly hit the ball, right? But if you hit the ball properly, you may not get a run also, unless you find a gap in the field, right? So the gap in the field is provided by the kinematics or the phase space. So when you hit the ball, for the ball, some phase space has to be available to get a run or two effectively. So to get a successful run, you need a phase space in the field, and also you need to hit the ball. Hitting the ball part is actually the dynamics, and finding the space in the field, that is actually your kinematics of the process. And when these two processes are both are allowed, then a physical process is allowed. I'll give you some example. This Feynman diagram part will give you the information on the dynamics of the system. So this is very important. You learn the dynamics from this part. But kinematics also I have to discuss, because otherwise I will not be able to calculate the cross section. So please let me know some if you have some more question.
Students, if you have any questions, please ask Professor Alam.
And anybody has any question, let me know.
So I want to ask a question.
Please.
Dikta Pratham Mukhopadhyay.
Yes, please.
Yes. So when we'll study the interaction tomorrow, then what will be the changes that will come in our equation? Like here we are studying only no interaction, only free particle movement. Then we can use this. Yes.
Right. So that's a good question. So the Lagrangian which I have written today, or I have been discussing for the last few days, is the Lagrangian which corresponds to the free particle. Okay.
Yes.
Or free field. So I have to add the interaction part to that Lagrangian, so that I get the interaction Hamiltonian. from the interaction Lagrangian, I'll get the interaction Hamiltonian. That interaction Hamiltonian HI, I'll put in the scattering matrix and calculate the interaction. Okay. And when I write down the interactions, we'll have some guidelines, like we are working in 3 space and 1 space, 3 space and 1 time dimension. So it is a 4-dimensional space.
Yes.
So I'll tell you that this 4-dimensional space will guide us to write down the interactions which will be renormalizable. I'll explain what is renormalizable.
Oh, okay.
That will guide us.
Yes. Okay. Thank you.
There is a question here. Is there any connection between quantum field theory and quantum chromodynamics? From which part connection comes? What I am discussing actually is the scalar field theory, and now quantum, scalar field theory, and then QCD, quantum chromodynamics, is certainly a quantum field theory, which is called the non-abelian gauge theory. This electrodynamical process, this quantizations of the Maxwell equations and all, that will give you a field theory which is abelian field theory, and quantum chromodynamics is non-abelian gauge theory or non-abelian quantum field theory. Certainly it is a quantum field theory, but that is much more complicated, which is there in our advanced course in our center. That actually I have this year I have taught, and this is almost going to end. So if you are interested, this online course, later you can join. So answer is yes, it is certainly a very complex and rich quantum field theory. Quantum chromodynamics is a very rich, very complex quantum field theory, much complex and rigorous than what we are discussing, or much rigorous and complex than your quantum electrodynamics or abelian gauge theory.
So one more question is, Ritubrata Mukhopadhyay speaking.
Please.
How much are we going to cover in till the 9th lecture? Will we cover entire abelian gauge theory, or we will not be able to?
Now, abelian, see, the almost within this 9th lecture, what will happen, I guess, this is 6th day, right? We have 3 more, right?
Yes.
So I'll be certainly able to do the grammar of the quantum field theory is almost going to be developed by next 2 lectures. Now that HI, the interactions, if you put the interaction from the scalar, you will have this scalar field theory. There, with if you can put the the interactions for the electrodynamics or quantum electrodynamics, you will have the process or scattering matrix for the electrodynamics, quantum electrodynamics. That the point is that what we have quantized so far is the scalar field, and if you want to study the electrons, they are fermions, so you have to quantize the Dirac field. Now there are all these commutation relations. There are some salient difference, like these commutation relations will become anti-commutation relations and all that, and that itself, I mean, within 9, if you want to properly develop the quantum electrodynamics, it will not be possible, because that will take some more time to discuss the Dirac field itself, because that discussion will take some time. And and one of the students, he said to discuss about the path integral. That is a very, it's a very strong technique in quantum field theory. That I am afraid, it will depend how long we can continue. Yes. But within this 9th may not be possible, but or I can introduce it, but just I will introduce it.
But if we want to study more, can that be made possible? That is another question.
Yeah, that's a good point. But then you and me, you have to talk to the organizer also. Mehdi Kalam, Professor Abdul Khan, and Professor Mukleshwar Rahman.
No, of course we can extend it, no problem.
Okay. We
No
actually
problem.
the first phase, and we are supposed to request you to extend further. That
Yes,
is
like
Okay,
10 more lectures.
we'll see then, because okay, from my side there is no problem, because I'm
Oh,
also
I see.
taking this advanced course, so I can take no problem. Only thing is, sometimes what happens in the working days, if I am little
Yeah.
late, then there is a problem. Otherwise, Saturday, Sunday, I have no problem.
Oh, I
we
see.
think that the beauty is yet to come. Actually, we
Yes,
just
yes,
the
that is
grammar.
Yeah.
I'm just developing the grammar of the, because field theory. I could have completed in line lecture, but something that will not neither satisfy me nor you. So
No,
yes,
no,
true.
no. Of course.
Definitely, of course.
You take time. That's no problem.
okay, so that issue I will discuss. What are the, after we finish this 9, then we'll see what are the other topics the students are interested. Somebody said about the path integral formalism. I will be happy to discuss that. And also, there are requests to give some problem. I would say that whatever I have discussed so far, please work out that fast. And then, of course, when we'll discuss, calculate the Feynman diagrams and all, we'll give a lot of problems. You can do it.
Yeah.
Okay.
Okay. So, any other questions?
Mahmood, you can conclude.
Yeah. Yeah. Yeah.
Oh, Mahmood is there.
Yeah.
I think he had requested me to share the full screen, but Mahmood, I somehow could not do it from the first day in my Mac. I don't know. I am not very, this part I am doing this online lecture doing fast, and in many of the cases my daughter is helping me. So,
Okay.
but I tried my best to share the full screen. I could not.
But it is fine, no problem.
Okay. Okay. Thank you.
So, so finally, I want to conclude that today's sixth lecture is over, and probably the next three lectures we will attend, and the participant will benefited from the other lectures. And as discussed, Professor Kalam and Dr. Khan, that the program may be extended as per the requirements of the students. And today I conclude that the session is now is over. Thank you very much.
Thank
The
you. Thank
Professor.
you, and good night to everybody.
Good
Yes,
night.
and good
Thank you.
night to
Thank you.
everyone.
Good night to you, sir.
Thank you
Thank
very
you.
much.
Yeah. We'll meet on next Friday.
Next Friday. Okay, okay,
Yeah. Yeah.
okay,
Okay.
okay. Thank
Same
you
Thank
very
time,
you.
much.
same 30.